Good morning, everyone. Thanks for coming. It seems to be the appointed hour for our talk. Computing in the 1960s. So the intent is to describe a little bit of what it was like almost 60 years ago, around the time I started. And what I hope to do today is to share with you my recollections of what it was like to be a programmer back then. So during the talk, I want to show you some of the hardware we had to work with, describe some of the system software we had to work with, and offer just a few personal anecdotes en route. So let's go back to the days of punch cards, punch paper tape, unit record equipment, and disk drives the size of a top-loading laundry machine. That was the drive. That wasn't the disk. That was just the drive. But I'd like to start even farther back, just to put a little bit of perspective on this. Roughly 1885, and we're now dealing with my grandmother's era. So this time is actually quite real to me because I've heard stories through my grandmother. A Hollerith punch card looked approximately like this. 45 columns, round holes, that turns out to be important. One corner cut, always useful in case you have a card backwards. You can find it quickly. The size of the card was not arbitrary. It was chosen to match the size of US currency of that era. And therefore, we could take advantage of existing drawers, etc. We could use office equipment. Now, the punch card that most of us are familiar with was introduced in 1928, kept the same dimensions, but now the holes were rectangular, and that was patented. Yes, patented rectangular holes. I know. It seems amusing, doesn't it? Yes, patented rectangular holes in 12 positions per column. There were 80 columns. The fragments that are punched out are known as CAD. How important was the punch card? I found this statistic incredible. As late as the mid-1950s, punch card sales made up 20% of IBM's business and 30% of the bottom line. The main competitor for IBM at that time was Remington Rand. Their holes were ovals. Their card was 45 columns times 2. 45 across at the top and 45 across at the bottom. That's a Remington Rand punch card. Until the early 1990s, people from IBM used to use punch cards for speaker notes because they fit very conveniently in a suit coat pocket. This is what we used to make punches in punch cards. We refer to this as a model 026, even though technically it's just an IBM 26. It looked like this, uppercase only. Uppercase only. If you had a typo, that was fatal. You had to throw away the card, start over. But occasionally, depending on what kind of typo it was, you might be able to duplicate all but the mistyped column, make a correction, and then duplicate the rest. It's hard to see in this picture, but there's a little box at approximately the right knee. That's where the CAD was. And you had to be very careful when you emptied that little drawer because they were highly flammable, and potentially could actually explode because of the ratio of air to combustible material. We were very concerned about fire protection in that era. Here's a bit of a closer view. and I found a little bit of film. There was a model 024 that was essentially the same machine, except it did not print onto the punch card. Here's a bit of a demo.
And then we can show that when they were duplicated, they both came out exactly the same.
Yeah, okay, that's good. Okay.
That was a program control, so it uses.
So it turns out that punch card media lets you get away with some really cool tricks. So consider the following code on a punch card, okay? Just one line of code. Now, BCPL, I believe, was the first language that used the double slash for comments. Now, imagine what happens to that card if you take it out of the deck, rotate it 180 on the vertical axis, put it back in the deck. Now the same card says that. I remember I once told that story to a class of freshmen, and the young lady sitting in the front row, she raised her hand so quickly I thought she was going to dislocate a shoulder. She said, "Sir?" I said, "Yes." She said, "But the slashes will be backwards." No, the holes don't change. Here's a bit of a story, because punch cards could be frustrating. We were once debugging a program that would only sometimes fail. See, some things don't change, right? Program that sometimes failed. In those days, debugging could take days. This problem did. The team was driven to despair. One guy started to watch the punch cards against the sunlight. Turns out there was one card that had a thin spot. And on a very dry day, with no humidity in the air, the card reader would sense that spot as a hole. Card replaced, problem solved. It took days. 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 Another piece of equipment that we used heavily was an 082 card sorter. This particular one dates from 1949. What this really is, although nobody recognized it at the time, this is a hardware implementation of radix sort. If you wanted to sort a deck of cards, let's say numerically, you ran it through once per digit, starting from the right. And of course, you had to assemble them very carefully, face down in the correct sequence, and run them through again on the next column, and then on the next column and the next column. If you're doing an alphanumeric sort, because letters were at least 2 punches per column, you had to run it through twice per column, once for the digit punch and once for the zone punch. The zones were known as 12, 11, and 0. This was all referred to as unit record equipment. And these machines were typically hardwired in the early days for specific applications. But then control panels became available. They were introduced by Hollerith himself in 1906. Removable control panels were introduced in the 1920s. And this was wonderful because applications could be wired on separate control panels and inserted as needed. This was programming. They were used when the machine's different applications required rewiring. This is what we're talking about. This was programming. This particular one dates from about 1948. Notice, of course, the patch cords plugged into what were variously referred to as hubs, jacks, or sockets. And by the way, these things were heavy. It's hard to tell from the picture, but that handle is sized for 2 hands. This is what it looks like from the back. Nobody enjoyed this, but that's what the technology was. The plug board was a spaghetti-like array of cords and plugs that tell a machine what to do. Move information here, do that action on that output, and so forth. These control panels were nightmarishly constructed Gordian knots of complexity and confusion. I'm fond of that phrase. They were slow, time-consuming, and above all, expensive. Here's a picture of what was referred to as an accounting machine. But even with all their complexity, they were considered a huge advance, because for the first time you could use a machine for different applications simply. Swap out the plug board. Before then, it was common for an entire machine to be broken apart and then reconfigured so that it could solve a different problem. And here's an example of what I have in mind when I say this. Vannevar Bush in 1931 constructed a machine called the Differential Analyzer. This was an electronic version of a differential analyzer that was constructed, I think, by the Thomson brothers in the UK in the 1880s, I believe. One of the Thomsons was later known as Lord Kelvin. And this machine, which was, you have to understand, by this era, calculating had been solved. We weren't yet in the computing era, but we had machines to do basic arithmetic. But what everybody wanted to do was solve differential equations. Because if you can solve differential equations, you can make war and do ballistics. Everybody wanted to solve differential equations. That's what this machine is all about. Vannevar Bush was an incredibly influential individual. This is just one of his accomplishments. He's also a gifted administrator, it turned out. So now let me tell you a little bit about the first computer that I ever programmed in a fashion that we would today consider programming. It was an IBM 650. It was marketed by IBM roughly in the 1950s, early into the 1960s. It was a decimal machine. It used biquinary encoding. It had a 10-digit word length, decimal digit. Main memory was a drum, roughly 4-inch diameter, 16 inches long, rotated at 12,500 RPM, and the capacity was either 10 or 20,000 digits, depending on what you paid for. It rented for about $3,200 a month, which was the price of a luxury car back then. All I ever learned about that particular machine was its machine language, not assembly, machine language. I had about 6 weeks with it. I was never allowed anywhere near the machine. And unfortunately, I really don't recall much else about it. By the way, for those of you not familiar with biquinary, it's been around for a very long time. You may recognize this incarnation of biquinary encoding. The bi is at the top and the quinary is at the bottom, right? Okay. The IBM 650 weighed more than 5,000 pounds, depending on how it was configured. Here is one image. And I found this little cartoon. No, this is not about me, but it could have been. I know it's not me because I don't smoke. Now, soon after was the advent of core memory. There's actually an interesting story there. Core memory was covered by 4 separate patents. And there were incredible lawsuits as to who actually got to claim the credit for inventing core memory. The lawsuits were ultimately resolved when IBM bought up all 4 patents. One of them had been issued to a gentleman named An Wang, who used his $500,000 from IBM to found Wang Laboratories. And that's the origin of that. Consisted of tiny donuts of magnetic material strung on multiple wires in an array. Each of the toroids corresponded to a single bit. Yes, it's a hardware bit. And it was magnetized in one direction for a 0 and the opposite direction for a 1, and there were different conventions depending on what machine you had. Some of the wires were used to select the bit you wanted, and others were used to read or to write the bit. Manufacturing core memory was a delicate job, almost invariably entrusted to women because they allegedly had steadier hands, using microscopes to thread thin wires through holes about the diameter of a pencil lead. This is what we're talking about. The scale here is roughly 1 millimeter. That's memory. Core memory very rapidly became the dominant memory technology because it was far more reliable and much longer lasting than vacuum tube technology, often referred to back then as valves, that were used by earlier machines like the ABC, the ENIAC, and the Colossus. Over a period of roughly 20 years, the cost declined from about $1 per bit to a penny per bit. And it was finally supplanted roughly 1975-ish. Of course, not all at once, but roughly at that time, we got semiconductor technology. And I recall that semiconductor technology baffled a number of service technicians. Because if you had core memory, you could power off and power back on, and your memory was still there. It's just magnetized. The magnet is still there. Semiconductor needed power. Turned it off, everything's gone. And the techs weren't used to that. I just spent an hour loading a diagnostic program from paper tape. What happened to it? Well, you turned off the power. So, you turned off the power. Oh, yeah, I remember that conversation very well. As late as 1979, I remember paying $5,000 for 128K, yes, K, of memory for a PDP 1145. And what I got for $5,000 was a back plane with space for 9 circuit boards, each of which, 8 of them were roughly this high from the table, and one, which was the parity circuitry, was only about this high. And I got a separate power supply for that back plane, and of course the circuit boards. $5,000 used. But you know, the nomenclature is still with us because to this day, capturing a memory image is still referred to as a core dump. Although we haven't used core now for what now, 40 years? Here's a different machine that I got to know extremely well, the IBM 1620, marketed as a small scientific computer. Small. It's the size of a desk. Here's another view. The lower covers are removed to give you a little bit of a better idea of what it's looked like inside. And here's one more view from the back with all the covers removed. And this picture happens to also include an image of a Model 1627 drum plotter, which is sitting on top of the cabinet. The technology of the era was what we refer to as discrete components. And of course, that was later superseded by integrated circuit technology. But we had to sneak up on integrated circuit technology because first we had SSI, small scale integration, later medium scale, large scale, and very large scale. But to give you an idea of how impressive that was at the time, I don't know if you recall the name Alan Perlis, who was the recipient of the first Turing Award. Think of it. With VLSI, we can pack 100 ENIAC computers into 1 square centimeter. Very impressive. The ENIAC might have fit into this room, but I wouldn't take odds. Just to give you an idea. So back to the 1620, the size of a desk. It had a built-in sprocket feed typewriter. This was wired into the desk, right? It came standard with a model 1621 paper tape reader at an astonishing 150 characters per second. You could get a 1624 paper tape punch at an astonishing 15 characters per second. And here's a closer view of those peripherals. Obviously, that's the paper tape reader, and there's the paper tape punch. I really don't know what it's doing on the floor, but it was there for the photograph, I suppose. If you're not familiar with paper tape technology, this gives you a little bit of an idea of what that was like. This is a 7-track tape plus little holes in the center for a sprocket feed. Okay. This image is misleading in one respect. The explanation uses hex. We never used hex back then. Everything was octal. Of course, octal is the same as hex if you just knock off a bit, same thing. And to this day, I still think in octal. Every time I want to change the read-write permissions on a file, chmod 777, octal, world read-write execute. It's just second nature to me. Of course, there were other peripherals available as well. Here's a picture. I have a little bit of a problem with this photograph. Whoever assembled it, I think, did a little bit of damage. The card reader punch was not bigger than the main console, certainly not taller. But this image gives the wrong impression. But nonetheless, we had a card reader and punch, which is really 2 machines under one dust cover. The console itself, and what we called an expansion cabinet, the storage unit. Please notice there's no disk inside. There's no printer inside either. You had the console typewriter if you needed printed output at about 10 characters per second. Let me share with you a little bit of the architecture of a 1620. The smallest addressable memory unit was a 6-bit digit. 4 of the bits were used for BCD, binary coded decimal. A 5th bit was used as a so-called flag bit, and the 6th one was a check bit. We were all very concerned with parity back then. A memory address consisted of 5 digits. And of course, that gave you an address space of 100,000. But to the best of my knowledge, no machine was ever sold with more than 60,000 digits of actual memory. It was just too expensive. The first 20,000 were housed in the CPU cabinet itself. The next 20 or 40 were housed in the expansion cabinet that I just showed you earlier. The memory cycle time was 20 microseconds per digit in the Model 1. There was a Model 2, which was considerably faster. The cycle time was 30 microseconds per pair of digits. The cabling, some of the cables were as thick as your wrist. And of course, they were a tripping hazard, so we kept them under the floor, which was raised for that purpose. Machine room routinely had raised floors and was heavily air conditioned. Typically, we kept the room at about 68 degrees Fahrenheit. So most of us wore sweaters almost all the time. The 1620, the machine language, every instruction with only 2 exceptions. They were 12 digits long. There's a 2-digit opcode and a pair of 5-digit operands, which we refer to as the P and Q operands. Instructions had to be left aligned on an even address. I don't remember what happened if it wasn't. We just never did it. The only 2 instructions that were not 12 digits long, one was a branch instruction, which only needed the opcode. I still remember, it was a 49. I don't know why I know that. But you only need one address for a branch, you know, the target where you want to branch to. And the only other instruction that was not as long was 42, BB, branch back, which we would today pronounce as return. Right? Go to the hardware register, find the return address there, and return. Okay. You could only call 1 level deep using hardware. There was no stack. You wanted more than that, you had to build your own. The operands typically were memory addresses, but we had immediate opcodes, so we could use one of the operands for a value of up to 5 digits. If an address had the flag bit set on the rightmost digit, it was an indirect address. And you could do indirection arbitrarily deeply. Set the flag bit here, get the next address. If it had the flag bit set, get the next address. If it had the flag bit, and so on. Okay, that was nice. But of course, it was a special feature, which meant they charged you extra for that. It turns out that running the program generated a lot of radio frequency noise. And if you had an AM radio, you could actually listen to your computer as it executed your program. So somebody once wrote a program that generated frequencies on demand, and you could actually play music by supplying data to that program. I don't know whatever happened to that program, but it was a lot of fun. The machine word was variable length, at least 2 digits, but you can have 60,000 digits if you wanted. I remember once I wrote a program to calculate pi to 30,000 digits, and it fit comfortably in memory. So I had a word that was 30,000 digits long. You addressed from the right, and it continued to the left until you found a digit whose flag bit was set. That marked the end of the word. Okay? If the rightmost digit was flagged, that was a negative number. That was your sign bit. If you needed characters, you used a pair of adjacent digits. Okay? This is before ASCII, but it did correlate somewhat with the holes in a punch card. For example, 41 through 49 was capital A through a capital I. And on a punch card, those particular letters all had a 12 punch on the card, which is the upper row. Okay? 51 to 59 is J through R, and so forth. Those all had an 11 punch. The Model 1 didn't have much circuitry for arithmetic. During its development, IBM had codenamed this machine Cadet. And the combination of those 2 facts led to a retronym. Cadet, can't add, doesn't even try. Okay? So how did it do arithmetic? It did it by table lookup. And you had to load the tables. It was about the first thing you did after you turned on the machine. Today we talk about booting up a machine, and boot, of course, is short for bootstrap. We didn't use that vocabulary. It was known as a cold start. So you loaded a cold start card, and then the very next thing you put into memory were the add multiply tables. Okay? And it still can't do division. Add, subtract, multiply by table lookup. And by the way, that table encoding was patented. I didn't know that. I needed to do coding in base 6, so I reloaded the tables. And one time I ran my software and forgot to reload the tables when I was done. And the next person using the machine was doing some, I believe he was a geographer, geologist, and he was doing some crystallographic analysis. And I remember him bending over the machine, looking at his results as they were being typed out, and he thought he really discovered something. I just hadn't reloaded the proper add multiply tables. So he was getting results in base 6 and he didn't know it. Division was always accomplished by subroutine, or if you paid extra, you had the automatic divide special feature. You have to understand, IBM were masters of marketing. It was the only company, or at least the first company, where if you called for service on your equipment, the person who showed up was dressed in coat and tie. And the only concession was that they were allowed to wear short sleeves instead of long sleeves. That's how IBM made their reputation. Hardware floating point was another special feature, which we used to emulate in software. And of course, this all predates any IEEE standard. A floating point number was a pair of adjacent fields. You had 2 digits for the exponent and I think a variable length for the mantissa. Here's a closer view of the console. It was designed so that we could actually watch what was happening inside. A couple of interesting things. Yes, there was an emergency stop in case of fire, for example. You pull the button. You pull the, I don't even remember what it was. I remember you had to pull it. We kept all the freshmen away from it because somebody invariably would try to pull it. There was a group of what were known as sense switches, and there was coding so that you could detect whether these switches were on or off independently. I remember making heavy use of them. One of my early programs was a program that played the card game cribbage. And I had one of those switches as a cheat switch that let me get extra output as to what the actual calculations were. Very handy. There's the MAR, the memory address register and selector. You could actually select what you wanted the lights to display. Here's a close-up of what that looked like. So let me play for you a little bit of what it was like to be in the room when an IBM 1620 was operating. You'll hear a little bit of talking in the background as well. People didn't know they were being recorded at the moment. But listen to the ambient sound, if you would.
Hey, this is making a little movie here.
And it was like that all the time. All the time. So at some point, we got some more peripherals. This was an IBM 1403 line printer, one of the best of its time. It could print up to 1,100 lines per minute, either 120 or 132 characters per line, depending on what model you got. The cabinet was incredibly heavily soundproofed. This was loud. And it relied on continuous form, pin-fed paper, typically 14 7/8 by 11, green bar paper. Of course, it could print checks if you had special forms and so forth. There was a large industry that specialized in printing custom forms. So here's what it sounds like in action with the covers open. Yep, went too far. Now let's do it this way. See the guy cover his ears at first? Okay. This is why there's an ASCII code called vertical tab. Think about that, vertical tab. You could go from one line to a different line on the page in one character. Vertical tab. I don't think anybody's used that in decades, but that's why it's there. Let me talk about another peripheral. We finally got disks. The IBM 1311 disk drive. That's what it looked like. Now, you can't see all the interesting parts, but at the back, retracted in this image, was a set of what we refer to as the read-write heads. They were arranged sort of comb-like, and they would move in and out in an operation that we referred to as seeking. And we were all very cognizant of how long it took for the heads to seek to the correct so-called cylinder on the disk. And even if once they were at the correct cylinder, typically you had to wait for a half a rotation until the data you really wanted to read or write came under the head. So we were always talking about rotational delay as well as seek time, okay? Well, the drive used a removable disk pack, which looked like that. And you could take them out and put a different one in. And we would do that routinely. A disk pack consisted of 6 platters, 14-inch diameter, 10 recording surfaces, capacity of 2 million digits per pack, which of course was 1 million characters. And you could have up to 4 drives, one of which was designated the master, and the other 3 were considered to be slaved drives. And there were 10 read-write heads, 1 per recording surface. Okay? The only thing the drive did is rotate the disk and provide the read-write heads and, of course, the control circuitry. One interesting feature of these disk drives, because the read-write heads were constantly in motion whenever the device was in use, there was an awful lot of vibration. And over the course of a day, this box would walk across the floor. So it was not uncommon for us to come in at 8 o'clock in the morning and find the disk drive was not where we had left it overnight. And so we used to, first thing in the morning, you walk in, you unlock the door, you go in, you check everything. Oh, and we would push it back by 8 or 10 inches with what we referred to as a hip thrust. What did we have for system software? We had Fortran 2, which was a compiler that we loaded from punch cards and later from the disk. We had Gotran, which was a Fortran-like language. It featured load and go programming, which was what made it useful. SPS is what we would today refer to as assembly language. And when we got a disk drive, we got Monitor 1, a single-user disk-based operating system. This, of course, still predates any form of time sharing. But I was a great fan of Monitor 1 because I remember one of the early things that I did was find the routine that controlled the disk drive and noticed that the algorithm that it encoded was first come, first served. Strict, simple queuing. So it would serve requests in the order they were received, which meant, of course, it had to seek all over the place. So one of the very first things I did was change that algorithm and sort the requests by cylinder number. So seek distances were dramatically, and I got some dramatic throughput improvement that impressed the dickens out of my bosses. So that helped to make my reputation back then. When we coded in Fortran, we used fixed fields, and some people actually sprung for custom printed punch cards that looked like that when they were blank. Here's what we had to do. Column 1 was reserved. You either put a C there or you left it blank. C was a comment. Columns 2 through 5, that's where you could put a numeric label. Column 6, you either left it blank or you punched something in there, often an asterisk, to say this is a continuation line. 7 through 72 is where you put your Fortran statement. And Fortran was still all uppercase back then. And 73 through 80, optionally, you could put a sequence number there. In case you dropped your deck, you ran it through the card sorter, you could put the cards back in order if you put the numbers there in the first place, which not many of us actually did. So let me tell you a little bit about Fortran idiosyncrasies from that era. So here's a very short Fortran 2 program. So please notice this little block of code, which is duplicated down below with one line in between. So these 3 lines together would produce that output. Okay, fine. The same 3 lines down below would produce this output. And the only thing I did in between is call swap on a pair of literals. Yes, today we say, oh, of course, that's call by reference. It's a dumb way to do call by reference. You don't really want to do that on a literal, but it worked. And of course, nobody understood call by reference back then. I don't think we even had the nomenclature for it. But that's what the compiler generated for you. I remember showing this to a relatively experienced programmer at the time, and he said, "What did you do?" I said, "This is what I did." I didn't know that worked. Well, it shouldn't. He was convinced I broke his computer. Another little idiosyncrasy. This is Fortran 2 code that starts a loop. It's so-called do loop. So this does 100 iterations through a counting variable here named I. And the 10 refers to a label for the last statement in the body of the loop. Okay? So do the following from here up through the statement labeled 10 and iterate through it counting I equals 1, 2, et cetera, et cetera. And by the way, it's a post-test loop. You had to do this at least once. While hadn't been invented yet. We didn't know how useful that was. Okay? So as I just said, the loop's body follows on subsequent lines up through the statement labeled 10. Now, this is the same statement, except I've changed one character. This is now an assignment. Huh? Yeah. It updates a variable named do10i, gives it the value 1.1, because spaces were not significant and therefore ignored. Idiosyncratic, yeah, that's one way of explaining it. By the way, that variable, do10i, that's going to have type real, because variables that weren't declared were implicitly typed based on how you spelled them. So if the name of the variable started with any of the letters I through N, which were easy to remember because that's the beginning of the word integer, right? So the in letters gave you an implicit integer typed variable, and anything else was declared real, which led to the phrase, God is real unless declared integer. We had no relational operators, just not part of the language, no logical operators, no truth values, and not even anything corresponding to a bool type. What we did instead was make use of the so-called arithmetic if statement. Here's an example. If x minus y 10, 20, 30, which does the following. Let's evaluate the expression, in this case x minus y, and then look at the signum of the result. We always pronounced it signum because sign was ambiguous. Maybe that was the trig function. So we always refer to it as the signum, the Latin word for sign. So if the result was negative, we would go to whatever statement was labeled 10 in this case. If it was exactly 0, we'd go to 20. If it was greater than 0, we would go to 30. Excuse me. So that's how we did conditional branching. Names in Fortran in that era were limited to 6 characters, which gave us a lot of naming puns like evaluate. The reason we had that restriction in Fortran is because there were a lot of machines that used 6-bit character encodings on a 36-bit word, which let you pack 6 characters per word. And 36 bits was considered valuable. They were popular for a couple of decades. That's enough to encode a 10-digit number. All right? And here's a short list of just some of the machines that featured that kind of encoding. In this era, there were 7 companies that manufactured the kind of large-scale computers we used to refer to as big iron. And we refer to these companies pejoratively as the 7 dwarves. They included IBM, of course, Univac, which later became Sperry. It included CDC, Control Data. It included Honeywell. It included National Cash Register, NCR, and so forth. They all were in the big business of computing. But there were lots of character encodings. None of this had yet been standardized. So we had 6-bit BCD, we had 6-bit ASCII, but of course this long predates lowercase. Who needs lowercase? Multics used a 9-bit character and so forth. And we just coped with this. The idea of programs that you could port had not yet arrived. Totally foreign concept. The idea that you could run the same program on different machines unchanged total alien to us. Never thought of it. Okay, I'd like to share with you an anecdote. I've not publicly told this before. So it turns out that in Fortran 2 and later as well, in Fortran, you declare an array via a special statement known as a dimension statement. And there's an example. You say dimension A parentheses 10. Of course, that gives you an array of extent 10. And the lower bound by definition was 1. Okay? Fine. But it was very common to find people misspelling the word dimension with a T in place of an S. I don't know why that was the case, but it was very, very common, especially among novice programmers, and I dealt with a lot of those. But even experienced programmers would just say dimension, okay, T-I-O-N. But when you compile that, it compiled successfully. So we got curious. And through experimentation, mostly by freshmen, by the way, we discovered that perhaps to conserve on code size, we don't really know why, the parsing routine treated any token that was sufficiently long and started with a D and said, okay, you're a dimension statement, and just blessed it. So a whole bunch of the student body got together and a consensus was very quickly reached. And there was a time period when local student programs would routinely declare arrays using what was called a dumbwaiter statement. It's sufficiently long, it starts with a D. One of those programs escaped our environment. Somebody had I think a research program, computer program, that he shared with a colleague at another institution across the country. And I remember as an employee in the computer center, I took a phone call from a gentleman with a very thick Southern accent, Southern US. And he said to me, among other things, I thought I knew my Fortran, but I don't recognize this here dumbwaiter statement. And I didn't laugh, but it was hard. So I replaced his deck. But let me leave you, before I take some questions, let me leave you with a closing thought, if I may. Certainly not mine. Since the beginning, many people have worked on computing, and many have furnished elements that were important. What we each accomplish depends on not only our brains and energy, but also on the surrounds in which we work. But in a larger sense, no one invents anything. We build and extend a little with our friends and on the shoulders of others. Spoken by J.V. Atanasoff, who built the first digital computer circa 1939. The ABC, A for Atanasoff, B for Berry, named for the graduate student Clifford Berry, who helped J.V. Atanasoff build the machine. One of the proudest moments of my whole career happened in 1981, when I had the honor of nominating J.V. for an honorary degree and being allowed to present him when that degree was conferred. To my knowledge, this is the only surviving photograph. There's J.V. being hooded. That's yours truly, when he still had hair that was dark. The degree is being conferred by the president of the university. This was May of 1981. And with that, I thank you very much.